Hey everyone, welcome back to my channel. Today I'm going to talk about pore elastic stress responses in offset hydraulically fractured wells. The title itself is a doozy, so I'm not going to state it here, but I'll state it in the presentation. Please be sure to like, subscribe, and comment on the video. That way I can incorporate your feedback into future videos. Well, I hope you enjoy the content. Hi everyone, today I'm going to talk about development-specific modeling of hydraulic fracture-induced mechanical pressure responses in offset wells. As I mentioned before, the title is a doozy. This is written by Conan and Spicer from Real Energy Services. Objective: that the details, the latest advances in the development of the digital twin for the hydraulic fracture-induced pore elastic responses. The approach centers on simulating the mechanical stress fields induced by hydraulic fractures in a rigorous and computational efficient way. The work continues the effort to fully leverage poromechanics theory to build the understanding of mechanics of the saturated porous media that comprise of ultra-tight, unconventional development. And I'll mention in the next slide what exactly is a digital twin. What exactly is a digital twin? It's comprised of computational physics and model describing the pressure interference during hydraulic fracturing of a real-world multi-well pad. There's a reference to another paper which published the first version of a digital twin for modeling hydraulic fracture-induced pore elastic behavior. It set the foundation for simulating transient pressure responses by explicitly modeling 3D primary fracture geometries of both treatment and monitoring fractures, and the fully coupled finite element analysis implementation to build a predictive model required for pad-specific scenarios. There's some methodology here. The paper describes development-specific analysis from data acquisition through a complete process for establishing stage-specific fracture geometry and growth profile. Characteristic signatures of linear pore elastic responses in offset wells are demonstrated by numerical simulations. Dominant fracture azimuth is established by way of analysis, offset response magnitude. Macro scale and fine scale analyses were performed to establish individual fracture geometry and estimates for each stage. Temporal evolution of the pressure responses is then mapped to fracture geometry evolution to establish fracture growth curves. And there's a sensitivity to non-parallel fracture development, multiple cluster initiation or fracture swarms, and geologic heterogeneity. So there's pressure-based fracture mapping for hydraulic fractures. We'll first go on with the field operations portion of this. This makes use of surface pressure gauges, and the accuracy happens when there's a stress interaction zone with the monitor well, and it's well defined. This is achieved by isolating a single stage from all other stages along the lateral. Typically, this is done by setting a solid bridge plug and perf completions for controllable frac sleeves in case of a single point entry. So the figure below talks about surface pressure data collected from the monitor stage, and pink vertical bars here, that's indicating completion times for the offset well. And the inset shows a monitor and pressure detail overlaid with the treatment data. The result of the analysis is most reliable when the monitor stage is completed as a regular full stage. And that ensures that the monitor fractures are full or nearly incompressible frac fluid. It's also important to have a monitor plane in contact with the formation to assure that a pressure change is probed on a sufficiently large region to be representative of an overall change in the stress field. And then after completion of the monitor stage, the well is shut in and the surface pressure gauge is installed. The gauge is in direct pressure communication with the monitor stage through the frac fluid in the open well bore. For the data acquisition standpoint, the paper does emphasize that you need high resolution pressure data, and there's some signal classification that is clarified in the paper. For instance, pore elastic pressure responses need to be differentiated from pressure responses caused by direct mass transport or extensive fluid migration. The monitor pressure data is overlaid with treatment data from the individual stages. The process for quantifying early or nearly undrained elastic responses relies on quantitative measurement of the pressure signal initiation, magnitude, derivatives, and duration. So now we'll talk a little bit about the fundamentals of pore elasticity. There's a local stress equilibrium and fluid continuity equations. They need to be simultaneously satisfied. So you have the two governing equations here. where G represents your gravitational acceleration, rho represents your fluid density, then you have your volume minus specific fluid content, Q represents your fluid mass source term, and sigma equals stress. So there's no fluid phase changes, thermal effects, and body forces other than gravity that are being considered. Then you have additional governing equations here, where you have your linear elastic stiffness tensor, your Biot-Willis coefficient, your solid displacement field, your utility tensor, and reference stress. And then you have your fluid flux, where you have your perm tensor dynamic viscosity. And then you have a volumetric relation to relate fluid pressure and fluid content and volumetric strain, where you have the Biot modulus. And then you have your volumetric strain. So the reservoir is assumed to be in equilibrium. Your treatment fractures are assumed to be bi-wing planar fractures. Planar geometry is parametrized, and it's based on fracture length and height. Two adjacent fracture surfaces are closed, bearing the minimal horizontal stress and unfolding zero fracture volume. And to simulate treatment at tangential pressure is prescribed on the two surfaces of magnitude exceeding your minimum horizontal stress. Your net pressure shall impose a mechanical and fluidic boundary load. Then you have another governing equation here where N is the normal to the fracture surface pointing to the reservoir. As net pressure exceeds closure, the aperture and therefore fracture volume is created. In the surrounding reservoir, the stress state shall change instantaneously because it must satisfy the new balance of forces. The paper gives a figure here where the blue torus lines or the planes is representing where the compressive stress is reduced. As net pressure increases, it ultimately creates a tensile stress sufficient for rock to break and for the frac to propagate. Then the magenta represents the net pressure acting on the fracture surface, so that compresses the rock. So blue references the reduction in compression around the fracture tip, and magenta indicates compression. After completion, hydraulic fracture has a finite volume, and partially the proppant is supported to retain the aperture and permeability. The source term, or Q, is 0, and the overpressurization needs to be resolved through diffusion or leak off into the reservoir. So therefore, the interface between the reservoir and the fracture volume displacement, U and influx Q continuity is enforced with another governing equation below. R and C refer to the reservoir and completed fracture respectively. So this represents the difference in the reservoir and the completed fracture. There is an assumption of planar fracture geometry, which is shown in this figure over here, where it gives the parametric description of the planar fracture geometry that shows a small length to height aspect ratio, and then the other figure shows a large aspect ratio, and then there's a fracture-based coordinate system. As far as the numerical solver goes for the paper that it describes, it's fully coupled pore elastic 3D finite element method. For the sensitivity analysis, this displays the 3D position of delta X of the treatment fracture with respect to the monitor of fracture-based coordinates. So you have your treatment fracture and your monitor fracture just to give you how everything will be set up. And then there are some hydrostatic pressure plots that shows the pressure gradient along the monitor fracture in two horizontal slices of the simulation domain. The lines represent the contours of the stress field and the perturbation due to the presence of completed monitor fractures. So again, blue represents tensile, and then the magenta represents compression in this particular figure. But these were how the sensitivity analyses were set up. This is just giving you more demonstration of the sensitivity analysis, how the change in fluid loading is in respect to formation permeability, where you have different increments of time. So this is plotted against a perpendicular position with respect to the monitor. So volume specific versus your position, and this is how and with respect to different permeabilities, how your fluid loading changes. And the plots over here on figure 7 represent the hydrostatic pressure plots, showing the influence of multiple parallel fractures. There's a single treatment, there's a single monitor with 4 parallel equal-sized treatment fractures, then there's a single monitor with 4 parallel non-equal-sized treatment fractures, and the last figure, the bottom right, are 4 parallel equal-sized monitor single treatment fractures. Now we'll go on to the case study where there's the subsurface geometry of the wellbore trajectories of a wine rack configuration. And these are the parameters that give you what the case study is over. You have your zone well spacing of 250 meters, a vertical offset of 70 meters, stage length of 48 meters, a cluster spacing of 15 meters, and then well 2H, shown on the farthest of the figure 8, has 5 completed stages, but before completion of stage 6 on well 2H, there was a solid bridge plug set, so it's making it a monitor stage. And that's shown in the large red spheres in figure 8. Here's the data that was collected on the right, where you have directional drilling surveys, relative position of trajectory set by wellhead locations and elevations, and then you have clusters or frac port locations. I'll talk about the undrained pore elastic responses for the two cases. You have two scenarios where you have a theoretical case of all fracs of equal dimensions, and then case 2 is the practical case with the variation of length and height. And that's shown in the table on the right for the monitoring stage and for all the other stages of 1H. Here are the results for case 1 and case 2. You have normalized pressure responses on the y-axis with respect to different stages on the x-axis relative to 1H. The diamonds represent the varying fractures and the circles represent your equal fractures. Figure 10 represents signal magnitudes observed by the spheres plotted on stage locations of the fractured stages. So the bigger the spheres, the larger the signal. Then the rest of these results are mapping fracture dimensions as well as your fracture growth. In the mapped fracture dimensions, the dotted line on figure 11 represents case 2 and the solid line represents case 1. You have varying fracture length versus your height at your x and y axis, and then the different shades just represent at different normalized pressures for different stages. Then you have, say, figures 13 or 12 and 13 that have a combination of matching height and length contour lines for observed stages, and there has to be a convergence to a fracture length at a fracture height. So there's a common point that was identified for figure 13 at 120 meters and 310 meters for length, or for height and length respectively. And then this is for a macro scale where for the equal-sized fractures, we already knew that the height and length was going to be 120 meters and 310 meters. For the fracture growth, which is figure 15, the biggest takeaway here is that the length and pressure change for the normalized pressure is nonlinear. For the presentation, I want to say this again, please like, subscribe, and comment so I can incorporate your comments into future videos. I also put my social media handles below so you can reach out to me on those platforms as well. Thanks again for returning to my channel, and I look forward to meeting you in the next presentation.